So thank you, Evan, and thank you to the Cosmos organizers for inviting me to give this talk. So the title of this presentation is towards special purpose edge computing. So I'm going to start with the motivation of what this area is about, and then provide some thoughts on what challenges we face in this topic and some work that we've been doing. So we are all familiar with edge computing. This is very familiar to this audience. So I'm going to be very brief here. Um, as we all know, there's been increasing growth in IoT and mobile computing and 5G technologies, which have traditionally relied on the cloud. But many of these applications that are emerging are latency sensitive. They may be bandwidth intensive. They may have privacy issues, and furthermore, they may need robustness to network disruptions and so on. And edge computing has actually emerged as a technology that will bridge this gap between the end devices, which may be resource constrained, and cloud servers, which may be distant or may not provide you the necessary bandwidth. So with that, let me talk a little bit about special purpose computing trends. So for the longest time, most of our computing infrastructure has been designed to be general purpose. So that means Intel-like machines that are designed for broad use. They support diverse applications, interactive, batch, parallel, distributed, and so on. And OS techniques had evolved to support needs of these diverse applications. And with Moore's law providing lots of technology improvements, this has always been the way to go for many decades. And what I'm going to argue here is that that trend to build all infrastructure as being general purpose is coming to an end for any number of reasons. So there has been issues with Dennard scaling, and people have said Moore's law may not continue to give us the benefits we've seen for decades and so on. So for the first time, we have started seeing more special purpose computing infrastructures. And this has been made popular with the rise of GPU computing, and GPUs have been around forever, but in the past maybe 5-10 years, they have been increasingly used for scientific applications, for AI applications, and so on. Now that trend has continued, and now we see Intel CPUs with built-in FPGAs. There are all kinds of specialized hardware for network acceleration and so on. And cloud computing has actually started to reflect this trend. So when cloud platforms started off, they would offer you general purpose servers of different size. Now they offer you GPU optimized servers, FPGA servers, SSD optimized servers. You can pick between ARM and x86 and whatnot. So increasingly, you have to decide what kind of application you're going to run and pick a server that is hardware that's optimized for your application, and which is what we mean by special purpose, so that the servers and the hardware are no longer general purpose. Now, since this talk is on edge computing, I'm going to basically talk a little bit about how this trend has impacted edge computing. So edge computing resources are also becoming increasingly specialized, just as you have GPUs and network accelerators on cloud servers. You have all kinds of accelerators that have come out in the marketplace that you can put into edge infrastructure. One common use case for this is what we call AI on the edge, where you can actually run AI workloads or AI inference workloads on edge servers. And what is shown on this picture are a number of accelerators from Intel and Google and NVIDIA and Apple that are designed specifically to accelerate machine learning inference type workloads. Now, the interesting thing is these accelerators are very cheap. They cost anywhere a few tens of dollars to maybe $100. They are very power efficient. They consume a few watts, and they're designed for a specific workload. Typically, these tend to be AI workloads. So what this has meant is now you can deploy an edge infrastructure with this specialized workload that allows you to tailor the hardware to specific applications and run that application very efficiently. So what is shown in this picture is essentially a toy example where you have a video camera that is streaming video to a Raspberry Pi device that has a Intel VDS or a VPU device, which is designed to accelerate computer vision workloads. And this low-end device actually, because of the accelerator, is able to provide performance that rivals x86 servers. And I'm going to show you more results later on in this talk, but there's a small table here which shows that this accelerator can provide you performance that's comparable to more general purpose machines. So the research question I'm going to address in this talk is, what are the architectural and research challenges that we will need to address as a community to realize this vision of a special purpose or a specialized edge computing infrastructure? So having provided the motivation for specialization, what I'm going to talk about is sort of an architectural overview or architectural implications of what this means for edge computing. I'm going to describe some research challenges that arise when you deploy these new architectures, present some experimental evidence that this kind of architecture does have some benefits, and then conclude. So let's start with the architectural implications. So what is shown on this slide is a traditional two-tier cloud IoT architecture, which is what most of the consumer-grade IoT devices that you can buy in the marketplace use. So this example here has Alexa, which essentially takes your spoken voice commands and sends it to the cloud for both recognition and execution. And it also shows you a camera that's designed for home security purposes that can actually stream video to the cloud, and you can do object detection and face recognition and whatnot. So this is how traditional IoT devices have leveraged the cloud by doing computational offloading. And we refer to this as a two-tier architecture. So you have the IoT tier and the cloud tier. Now, with the emergence of edge computing, this two-tier architecture has evolved into a three-tier architecture, where the edge actually sits between the IoT device and the cloud. And there are many examples of this now, again, with consumer products, where you might actually have a smart home gateway that acts as your edge server. Here we have an example where there's a motion sensor that gets triggered. It's then coordinating with the camera to only capture video feeds whenever there is motion, which can then be sent to the cloud. So which makes this whole process more efficient, and you only generate video data when there's something interesting going on. So this is a three-tier architecture where you have an edge that sits between the cloud and the IoT device, and the edge can provide some useful services, but with the assumption that the edge is still more resource constrained than the cloud. And there are many variants of this edge architecture. What I showed on the previous slide is just one of those many examples. So you have the cloudlet variant where the edge is not one small device, it's an entire cluster or a small data center that's deployed at the edge of the network. You could have this cluster being deployed next to your cellular towers in a 5G case, for example, when you have a 5G edge. You can also assume that it's not a single cluster that's deployed at the edge, but it's an entire distributed edge cloud, where you have lots of different edge sites that sit between lots of IoT devices and the cloud. So these are just many different variants of what is still a three-tier edge and a cloud architecture for IoT. Many use cases here, such as augmented reality, VR, and so on, that can offload its computations to the edge. Now, coming to specialization, what happens to these architectures is now you start taking these more general purpose compute infrastructure and start adding specialized hardware onto it. So here's an example of a two-tier specialized edge, where the edge node has one of these accelerators that's designed for accelerating AI workloads. So this was exactly that toy example I showed earlier in the slide, where you have a video camera streaming now to an edge device where you can essentially do inference. So things that were done in the cloud traditionally can now be done on the edge, because the edge has become more capable as a result of this specialized hardware. Now, if you look at the vendor sheets for these products, they claim that these devices can provide server class performance when they're added to an edge infrastructure. And later on, I'll show some results on whether this kind of claim is actually borne out by actual experimental evidence. So this is one example of a specialized edge infrastructure. But one thing we got to realize is the specialization is not limited to the edge itself. You could put these accelerators on the device itself. So that will essentially give you an IoT device with an accelerator. And there are many examples of this where the cameras can now perform on-device inference. You don't even need to send the data to the cloud or to the edge. By putting these accelerators on the devices, they become more capable and they can do on-device processing. So this is an example where both the device is specialized and the edge node is specialized. And you don't need to stop there. You can go back to our 3-tier architecture and assume that every tier is now specialized and hence more capable than a more general purpose architecture. So in this case, the cloud servers have GPUs, FPGAs that allow them to accelerate various scientific workloads or AI workloads. The edge clusters are themselves accelerators that allow them to efficiently support various types of applications. And so are the IoT devices, and mobile devices like phones also have GPUs on them, for example. So this entire 3-tier architecture has now benefited with specialized hardware being embedded in at all tiers. So to quickly summarize this architectural description that I gave, so we started with a traditional 2-tier cloud and IoT model, and then we looked at how this evolves into a 3-tier architecture with edge computing, and then a specialized 3-tier architecture with all tiers seeing some benefits of acceleration. And so the latter picture on the right is what I'm going to use for the rest of this presentation. So having described this architecture of specialization, let me talk a little bit about research challenges. So in a longer version of this talk, I actually have 6 different challenges, but because this is a shorter talk, I'm only going to go into 2. Let me start with cloud and edge economics. So as we know, cloud data centers have economies of scale where they have very large data centers where you have lots of servers at one location. And so in addition to economies of scale, they're designed to service peak workloads where applications can peak at different times. And because many applications are co-located at a single cloud data centers, you get statistical multiplexing benefits where this application can burst at different times, and you can then service those peak workloads without having to provision for the some of the peaks of all applications. And that's always been the case whenever you have economies of scale, whether it's in the network or at a large cloud data centers. Now, this particular figure on the right shows you a cloud data center with K servers that has been designed to service N applications. So now let's ask what would happen if those same N applications were serviced at the edge rather than in the cloud. So what you could do is you could take those K servers and you could split them into M different edge sites where each of those edge sites would have K over M servers. And you could also, assuming a very ideal load balance situation, you could take those N applications and also split them across sites. Now, because each edge site has much fewer servers than our cloud data centers, you don't get the economies of scale you had anymore. But more importantly, if you want to service the same kind of workload dynamics where these applications peak at different times, what happens is you actually need now more than K over M servers to give the same benefits of statistical multiplexing you get in the cloud. This is because you have less multiplexing and less smoothing benefits as a result of having fewer applications at each site. So what that means is the same applications that you had before need more than K servers split across M sites to provide the safe to be able to support those applications and their workload dynamics. So not only have we lost economies of scale, we also need to actually provision more hardware at the edge to see the same benefits of multiplexing you have at the cloud. Of course, you have lower latency to the edge, which is beneficial to the application, but from a provisioning standpoint, you are worse off because you need to actually put more hardware to serve the same number of applications. Now, I gave you an intuitive example or intuitive explanation rather of this argument, but there's actually a more formal way to show exactly this result that I presented here, which you can do using queuing theory. And I'm not going to go into the queuing theory way of making this argument here, but this is what all I want to say is this is not just a intuitive argument. It's actually borne out by how these applications provide statistical multiplexing when you have more servers, and how queuing theory allows us to show the benefits of latency, but also this multiplexing benefit. Now, from an economic standpoint, what this argument means is that providing edge service is actually going to be more expensive for that application than the cloud service. So an edge service provider will have to charge more for that application than if they had actually put them in the cloud. And whether applications will pay that premium because they also get benefits of lower latency is a market question, but it's something that we ought to be aware of when we actually talk about edge computing. Now, none of this argument had anything to do with specialization, which is really the focus of this talk. But what I'm going to say is when you add specialization to this infrastructure, everything gets worse, because no longer can you put any application on any server. You need to put it on a server that actually has the right kind of accelerators that are specific to your application. So that means that multiplexing benefits go down further, and which means that you lose even more in terms of economies of scale and multiplexing benefits. So this is an important research challenge that we'll have to address, but that lies at the intersection of technology and economics. Now, another challenge is from an application developer's perspective. The previous one was more a provider perspective challenge. This one is a developer perspective challenge. So we have now an infrastructure which is specialized at all tiers. Your device tier is specialized, your edge is specialized, cloud is specialized, and so on. So you can ask the question, where does your application code reside? Previously, maybe your devices were dumb and you streamed everything to a cloud or maybe to the edge, and all your entire application actually sat in one place. But that is no longer the case, because you might have to deploy some part of your application on the device. You may not be able to get rid of the edge or the cloud altogether. So a portion of your application may actually get deployed on the edge and the cloud. So this is going to make your application development more complex, because applications essentially become more distributed. They can no longer be put in one tier. They're going to be split or distributed across multiple tiers. So from a developer standpoint, that's actually more work, more complexity to deal with. You have to think about what functionality is going to reside at which tier, how to take your application and split it across tiers and so on. So this specialization actually has both a bearing on both provider economics as well as application programming. And so both are challenges that we'll have to address if you have to realize this vision of a specialized edge computing infrastructure. So with those challenges, I'm going to now talk a little bit about our experimental results. So here is the question I want to actually walk all of you through. So we started with a more traditional edge architecture, which is shown as a small cluster of rack on the right here. And then we are going to ask the question of whether a specialized architecture is somehow going to be better along some dimension than a more general purpose architecture. And in this case, if you actually look at these two pictures, you'll realize that we are really not comparing apples and apples at some level. What we are comparing is a standard x86 rack of servers, which is like a cloud-led data center, that's compared to something that's a cluster of Raspberry Pis, much less capable than a traditional x86 server infrastructure, but one that has been specialized. So this picture that you see, the photo you see here is actually a tiny cluster, which is 12 inches by 12 inches by 12 inches, that actually has Raspberry Pi class nodes with various kinds of accelerators. In this case, I think this is a Jetson Nano GPU cluster. The whole cluster consumes 90 watts for 10 nodes, which is less than what a single server on this rack of x86 server would consume. And you're really going to ask the question, if you have this very tiny low power edge nodes, how do they really compare with more traditional x86 infrastructure that you might deploy on the edge? And that's really what we want to think about carefully, given the benefits of specialization. Allows you all these new form factors that are very different from more traditional data centers or x86 architectures. So there's a picture at the bottom right, which shows you a slightly larger version of the one on the middle. And the one at the bottom is actually a 48 node cluster. It's still maybe 18 inches by 18 inches, fairly small footprint. Still has about 200 watts of consumption, but has 48 node cluster on it with gigabit Ethernet and whatnot. So let me explain the methodology for the next couple of experiments I'm going to show you. So we took all kinds of accelerators that are available in the marketplace, and there are 4 shown here. They're the same 4 I showed earlier in the talk. So we have the Intel Neural Compute Stick 2, which is a VPU or as a vision processing unit. We have Google Edge TPU, which is an ASIC device that accelerates deep learning inference. At the bottom, you have 2 embedded GPUs. The Jetson TX2, which is a slightly larger footprint GPU, and the Jetson Nano, which is really a Raspberry Pi class device with a GPU from NVIDIA on it. A small GPU consumes about 5 watts as opposed to larger GPUs. And what we want to do is compare how these accelerators can provide some benefits in an edge setting. So we have these 4. We are going to compare it to an x86 server and x86 server with the GPU. So this graph here actually shows us the performance of various accelerators that are shown in the middle with bars, with a Raspberry Pi to the left, a Xeon server grade CPU, and a cloud GPU on the right. The y-axis is throughput or performance of a deep learning inference model. It's in log scale, please keep that in mind. And then the x-axis is various devices. There are 2 color bars here. They are for 2 different machine learning models. But here, let's just focus on the red one, which is the Inception V4 model. It's not important what the model is. What is important to see is the middle red bars are all close to one another. So those are the 4 accelerators that are being compared to a Xeon class processor. And you can see that $100 device is giving you either comparable or in some cases somewhat better performance than server class performance. So if you go back to what I said earlier in the slide, many of these vendors that sell these accelerators claim that they provide server class performance. And we wanted to actually see if that is borne out, and you'll see that they are actually giving you performance close to a general purpose CPU. Okay? Now the rightmost red bar is actually a cloud GPU. And you will see that the red bar is higher than everything else. And since it's in log scale, that actually is an order of magnitude higher, not just a little bit higher. So what that says is if you put a GPU on a cloud server, you are going to get much, much better performance than any of these tiny accelerators. But if you just have a general purpose machine, you can actually give performance that's close to these, the accelerators, the performance close to a CPU. So the marketing just bear out in terms of some experiments that we have performed. Now here is a more interesting variant of the graph I showed you. We normalized that raw performance by power and by cost. So if you take the power footprint of these devices, you can take the raw performance on the previous slide and just get performance per watt. So now it's the same devices, same workload, but the y-axis for the left graph is not just throughput, it's throughput per watt. And for the right graph is throughput per dollar. So we took the cost of each of these devices and we essentially said, what's the throughput you're going to get for each dollar you spend. So now you see that those accelerators are vastly outperforming. Those are the 4 red curve bars in the middle. they're vastly outperforming a general purpose server CPU, and they're even outperforming the cloud GPU. So even though the cloud GPU had better raw performance, on a throughput per watt basis, these accelerators are actually going to give you better performance. And the same story is true for the figure on the right, which shows us what happens on a throughput per dollar basis. The economics of buying these devices is actually quite attractive. So what does this mean? From a provider standpoint, if the workloads that you're going to put on your edge infrastructures are ones where you can distribute them among lots of little devices, you are going to be better off putting lots of these accelerators instead of putting a small number of bigger devices or bigger machines. On the other hand, if you have large workloads that you want to, or applications that are heavy duty that you want to run on the edge, then these accelerators are not going to give you benefit. You're still better off going with your traditional architectures, general purpose architectures. But because many of these machine learning models belong to the former category, not the latter, if AI on the edge does become a reality, the role of these accelerators is only going to become more common and more attractive given some of these results. So with that, I'm going to essentially summarize what I said. So we started with the traditional model of edge computing, and I argued that this edge computing actually provides several benefits from specializations. I presented two challenges. There are many more, but I presented two key challenges. One that has to deal with the economics coming from hardware complexity, and the other that comes from higher application complexity that impacts the application developer. So those are challenges that we still need to address as a research community, but I did show some results that show promise of the approach overall. And I think I would like to end by saying that there are many software runtime language tools, as well as many other challenges that we will need to design to fully realize this potential of a specialized edge computing infrastructure. So I'm going to stop here and take questions, but I do want to acknowledge my students, Shanlen and Walid, who essentially did a lot of the work I presented here, and my postdoc, Ahmad, and my colleague, David Irwin, who's collaborated on this work. So thank you for listening. I'm happy to take questions.
Thank you very much, Prashant. So here we have a couple of questions. I think two of them are actually in the chat, panelist chat, right? I'm not sure if you see it. If you don't, I can read it. So the first one says, great talk, Prashant. What is your opinion on applying ML AI at the edge for latency sensitive mission critical applications?
Right. So that's a great question, and there is I didn't talk about any of this mission criticality here. So first of all, ML AI on the edge for latency sensitive applications makes perfect sense. When your mission critical applications, there's an argument to be made where if you do your compute closer to the point of generation of the data, that's always going to be better off. So in some sense, specialization actually allows you to do that. The compute is moving closer to the IoT device or the mobile device that's generating the data. So if your mission critical applications depend on good network and whatnot, or can rely on a good network, then you may not need to do this. But if you believe that there are going to be issues with the network dynamics, it actually makes more sense to put things closer to where the data is being generated, and it helps you build more resilient application. That's the observation we have made when we applied this work to more mission critical type applications.
Then the related question is sort of related to large data sets at the edge. Given the limited capacity, how does it compare to cloud? You know, should we push stuff towards deeper in the cloud, right?
Right. So I think that the thing that we want to keep in mind is I have not argued that all of the AI workloads should move to the edge. There are two broad classes. There's machine learning training and machine learning inference. Training does not have latency sensitivity. and they have large data sets. So either you should do this on the cloud or you should approach this with a federated model. I still believe that cloud is better to do the training. So the workload I was talking about here was inference, where the model is already developed, it's trained. You're simply feeding it data and asking it to make predictions, like recognizing objects or recognizing speech if you have like a smart speaker and things like that. So I think there's still a role for the cloud. I'm not arguing that the cloud goes away, but I'm saying that certain class of workloads are just better done using this type of edge infrastructure, and certain things will be better done in the cloud.
I guess that's what Carol is also pushing out as a argument, right?
Yes, I think that the takeaway is not that everything should be done in the edge. The takeaway is specialization allows you to do certain things very well at the edge, and those things should be done at the edge. Doesn't mean there are other things that are not going to be benefit from specialization should also be done at the edge. Those should still stay in the cloud.
Yeah. Yeah. So do we have any other questions? I don't see. Yeah, we just have a praise for the answers. So, and great insights. So I would actually thank Prashant for this great talk, and hopefully, if there are any other questions we collect over time, we'll certainly make sure to try to get answers from all the panelists if we can stay towards the end. Oh wait, there is one more question. About pricing mechanisms. I'm not sure if you see it on the Q&A, so let me read it. Considering the extra cost of developing edge services, do we need to design new customized pricing mechanisms to customize price based on QoS criteria of different applications to compensate the costs?
Yes, I think that the very short slide I had on economics indicated that the same pricing mechanisms you had at the cloud will actually not work at the edge for many different reasons. So first of all, if you think about edge, you can think of it as a more premium service where you're providing lower latency. So that by itself should allow a certain premium in the pricing. But from a provider standpoint, it's not just providing better performance, it actually costs them more to provide that better performance, because as I was arguing, you need to have the degree of over provisioning you need to serve a certain number of applications is higher in the edge because of lower economies of scale. So the cost, even if you don't think of it as a premium, the cost is actually going to be higher. So that means you need to come up with more innovative pricing mechanisms to make it beneficial to both the customers who are going to pay that higher price, but also allow the providers to get a good return on investment. So I think that there is a lot of open questions there as to what the pricing would mean. There will be new applications which presumably will allow you to come up with interesting pricing mechanisms as well.
Thank you very much.